So last week you found, or you were exposed to what is meant by fluid properties, what are the various fluid properties that could be important in fluid mechanics, right? So if you look at what we have been doing, okay, we took simpler situations and then we try to calculate how does the flow look like, right? The tube flow, the flow between two parallel plates. Then we talked about how the fluid properties are important and how it is important in determining the velocity profile. Now, you know that the equations that you used, okay, to calculate the flow profiles, they were really complicated. And they were complicated because on one hand they were partial differential equations, then they are also nonlinear equations, right? And therefore you had to make a whole lot of assumptions every time to simplify the equations. And then you did get some profiles, and you also found that that could be reasonable in certain cases, but they may not be reasonable always, okay? And the way, therefore, you should be attacking a problem, you just can't depend on theory always, okay? You need to look at other options, okay? There are two other options that come frequently, and one is to do a numerical simulation. In other words, you have got a partial differential equation, you have done numerical methods last semester, right? So you basically use any of those methods and try to solve these equations, okay? So that field is actually known as computational fluid dynamics. So that's one of the options. So one option that we have seen so far was essentially looking at the theory in which we try to get analytical solutions, but we may not be always able to do that, and then we could try doing CFD, okay? So the computational fluid dynamics. The other option, of course, is to see what's going to happen directly, and that is by doing experiments, okay? So these are the three options that you will have when you want to look at a flow problem. Now this is straightforward because you have already seen that these two, okay, there is an issue. The issue is that, let's say you are doing an experiment, you do it under certain conditions. Let's say you keep the temperature something, you take some particular liquid and do it, and then you find some solution, okay? You find some flow field, but you do not know whether that is always going to be the case. You do an experiment with water, now you change that to some oil, you don't know whether that is what should be expected. While in case of theory, you did not have a problem because the entire problem is defined in terms of certain parameters, okay? So is the case with CFD, okay? When you are doing a numerical solution, you will be doing it for a certain given numbers, okay? You are not actually solving the equations, you will be doing it for numbers. So both from CFD and from experiments, you are actually going to get numbers, not equations, and therefore those numbers are for a given set of conditions, and then you would not know how to interpolate or extrapolate for that matter. That's clear, okay? So when you are doing CFD or experiments, you are actually going to get lot of data. Now so when you get lot of data, okay, so let's look at a simple example and see what that means. Let's say you have some complicated shaped object, okay, and there is a fluid that's going to come with some velocity u, okay? So the fluid will come, it will go past this object, right? And your interest is in finding out what is the force that this fluid is going to exert on the particle. Or you could ask the other question, how much drag the fluid will experience because of the presence of the particle, right? The object is there, so it's going to put some restriction onto the fluid motion, which the fluid will experience as a drag force, or you could say that the particle is going to get, force because of the moving fluid, okay? Either way, you are interested in finding out what is that force, okay? So you are interested in finding out what is the force, let's say, exerted by the fluid on this particle that you have put there, okay? You would expect that it would definitely depend upon what is the velocity with which the fluid is coming. So you would say, okay, maybe that's a function of u, the fluid properties, right? What are the two fluid properties that would be relevant? Viscosity and density is the other property that comes into the picture. And then of course, how big the object is. It does not have any shape. Let's say that, some particular length, which might be some characteristic length of this object. Okay, let's say these are, so we expect that, okay, these are the things maybe that would be important, and you want to determine the force. What would you do if you were doing either, a numerical solution of equations, or if you are doing an experiment, you would choose a particular value of u, a particular value of mu, a particular value of rho, and a particular object, run the simulation or run the experiment and calculate the value of force, right? Now you would do that for various combinations, right? So for example, you could keep u fixed, mu fixed, L fixed, and you will change, rho fixed, and you will change L. Let's say you will change L, let's say 10 times, so that you can get it for large range of length. Okay, then you would keep u, mu and L fixed and change rho, and let's say you would change that for another 10 times, and you would keep doing that. Okay, so you will get huge, you have to do huge number of experiments or huge number of simulations to find what is really the dependence of force on something. So if you, let's say, for each of them, if you do 10 times, 10, 100,000, 10,000 experiments or 10,000 simulations you will have to do if you really want to find out what is the force that's going to look like. Agreed? That's clear. So and the problem is that one is that you need huge amount of resources, large amount of time, okay, and then you end up with a huge amount of data which you do not know how to really even represent, because you have things which are dependent on 4 things, okay, and then you basically end up with huge number of tables. So that's what is going to happen. So the question is there a better way of doing this? Okay, and that's what we are going to do, and that's what is called the non-dimensional analysis. Okay, so we are going to look at non-dimensional analysis. So we will see how to do non-dimensional analysis, but let me tell you what the result is going to be for this particular problem that we just talked about. For this particular problem, if you were to do non-dimensional analysis, you would find that this equation can be recast into F divided by rho u square L square is some function of Reynolds number, where Reynolds number is going to be L u rho by mu. Okay, so if you were to define a Reynolds number, which is the way to define it, right? The length times the velocity times density divided by the viscosity. So this is going to be a non-dimensional number. What will be the units of F by rho u square L square? It's non-dimensional. This is another non-dimensional number. Okay, so you get one non-dimensional number is equal to some function of another non-dimensional number. Okay, so that you can easily represent if you were to have, let's say, a graph. You will just say that, okay, I'll just plot F by rho u square L square as a function of Reynolds number. Okay, and then you will get some data, some curve. And that's all needed for this particular problem. You don't have to worry about 10,000 points and so on representing space, because the only quantities that are really going to matter in this case would have been Reynolds number and force, force divided with this particular quantity. So a particular form of force becomes a function of Reynolds number alone. You change fluid, doesn't matter. It's only what matters is only this particular curve which you would have represented as a particular function. Okay, so this is a nice way of representing things. It's very compact, and then you don't need to worry about how to do the extrapolation or interpolation. Clear? So the question is, how does one end up with such a relation? We may not know what exactly G is. Okay, the non-dimensional analysis is not going to tell you whether this is, this particular form is Reynolds square, or is it exponential of Reynolds, or is it sinusoidal of Reynolds. We won't get it. We will not know exactly what it looks like, but we will know what are the numbers that are going to be connected by a particular form of function. Okay, and that's all we care about, because that is enough in most of these cases, because things basically get into a compact form. Doubts? Few things which you are very familiar with, I'll just still tell. Principle of dimensional homogeneity. Okay, that means given an equation, each term in that equation will have the same dimensions. You all know that very well. Let's say S is equal to some S0 plus ut plus half at square. Okay, the equation describing the motion or the trajectory of a particle, right? S0 is the initial displacement, u is the initial velocity, and a is the constant acceleration, and this equation is going to tell you where the particle is going to be at a given point in time. What would be the dimension of each of them? S will have the dimensions of length, S0 will have the dimensions of length, ut will have the dimensions of length, meter per second into second, at square will have the dimensions of length. Okay, so all terms basically have the same dimensions, and that's known as the principle of dimensional homogeneity. How about Bernoulli's equation? P by rho plus half V square plus rho G equal to constant. Can you check what are the dimensions of each of the terms? P by rho has the dimension of potential. What is potential? What is the unit of potential? Work per unit mass. So can you tell it in terms of fundamental dimensions like length, mass and time? So V square is definitely L square T to the power of minus 2. Rho G, oh did I make a mistake? It has to be wrong, no? G is Z, yeah, correct. Right, and therefore this constant will also have the dimensions of L square by T square. So therefore, each of the terms have the same dimensions, and that's what is known as the principle of homogeneity. Few other things. So these are the other things that you will come up in any equation. Dimensional variables means some kind of variable that would have dimensions. For example, in Bernoulli's equation, it would have been pressure, density, velocity, any of them. Okay. Dimensional constant are constants which may also have dimensions. For example, gravity, gravitational constant, and so on. Pure constants, like for example the half we had there, okay, things like that. Okay, so these are the three things that typically come up in an equation, and pure constants are something which we won't really have to worry about throughout the dimensional analysis, okay, because we would never worry about that. We would be worrying about dimensional variables and dimensional constants, things which have got dimensions. Okay. So now before doing it, okay, we need to worry about one another thing, that is choice of variables, or choice of rather scaling parameters. Choice of scaling parameters. So see, we are going to have few variables, okay, in this problem of which when we talked about flow, okay, past some object, we said it's basically a function of rho mu u l. We need to identify some parameters to non-dimensionalize it, okay. Now, it would not be obvious what are the parameters that we should choose, okay, and it's basically, I mean, there is no way to really do it, but in order to see what it means, let's take a simple exercise where we already know the functional form, which is, again, we'll go back to this equation, S equal to S0 plus ut plus half, let's say, g t square, which should be the trajectory of a particle which is just falling under gravity, okay.